right, good afternoon, everyone. Welcome to Best Practices for Querying Vector Data for GenAI Apps in Postgres. I'm Jonathan Katz. Very excited to be presenting here today. This is my first live silent session, so bear with me through any of the challenges that may occur. But before we dive in, I want to just emphasize that this is an L400 talk. So we're basically going to get maybe just short of PG vector internals, but we're going to dive deep. And we're going to use the insights in terms of diving deep in terms of how PG vector and Postgres works in order to understand what are the best decisions you can make for your applications. So there will be a gentle ramp up, and we're going to go through a lot of data and charts, and I'm going to do my best to explain them to you today. The nice thing is that this will be recorded, so if there's things that you want to follow up on later, those will be available. And I'm happy to answer questions after the talk, because this is probably going to take the full 60 minutes. So why does this even matter? Why do we even care about searching for vectors in our database? And it comes to this example where we have a question comes in that might require some personalization. Give me some information about my order. And the amazing thing with these foundation models and these generative AI models is that we can give these rich, personalized responses. But we need to have a way to be able to take the data that exists in our databases and tie that into the personalized response that's coming from the foundation model, because the foundation model is probably not trained on the data that's existing in your private data sources. So an effective technique that's been developed to be able to deal with this is called retrieval augmented generation, or RAG. And the idea behind RAG is that it gives the ability for us to bring in that context we need to be able to give that personalized response. So typically a foundation model is just trained on publicly available information. So if you ask something specific, say, how much do these blue shoes cost, it's not going to know. But if you bring in, say, your product catalog, your pricing catalog, and all that information, you're able to then have the foundation model deliver how much those blue shoes cost. And that's the key. But we need to be able to we need to have a way to be able to take that data from our database and bring that into the foundation model. And there's different kinds of information out there. But information that's in an unstructured format, say raw text that hasn't been labeled, or images or video, needs to be represented in a way that we can search over it. Now, that's not necessarily new. We've been searching over text data for years. That's the whole thing of full text search. But if we're able to take a mathematical structure such as a vector and effectively wrap that around the text data, it gives us a way to be able to compare it through performing distance computations. And again, that opens up other kinds of searches too, like comparing text to images, text to video, images to video, because we have a common language effectively through the mathematical representation of the vector to be able to do that. So where do vector embeddings fit into RAG? The first part is ingestion, where you have some kind of unstructured data. It could be PDF documents. You likely need to prep it to be able to be used in something called an embedding model. The embedding model is what takes the unstructured data and turns it into the vector, and then you're going to store it somewhere, in this case today in an Amazon Aurora database. So that's the ingestion workflow. And then comes the fun part, which is exposing it to your application, and that's the agentic workflow. And in the agentic workflow, a user comes in and asks, how much do these blue shoes cost? We have to take that question and turn it itself into a vector to be able to get that context, so then we can query the database and find the most similar results to that. And then from there, we take that question and the context we put into the foundation model and turn that into a response. Now, talking about the whole RAG workflow in detail is the subject of a different talk, because today we're really going to be focused on what's the role of the database here, specifically Aurora. But if you happen to catch DAT423 later, we're going to talk all about the fun of the retrieval augmented generation workflow and where your data fits in. Now, vectors can be challenging, and this is actually what personally drew me to this topic. First off, we need to be able to generate the vector embeddings, and that can take some time. Generating, let's say even it takes 100 milliseconds, and I have 1 million vectors. Well, this is why we're going to need to store them somewhere, because 1 million times 100 is a very big number. I guess 100 million. A lot of the modern embeddings are fairly large as well. If you take a 1500-dimensional vector, that's a 6 kilobyte payload, and that doesn't seem like much. But if you think about data you store in a relational database, your average row size is probably less than a kilobyte. So in some ways, we may be having some data inflation here. And you might say, well, Jonathan, can't we compress that? We've been doing compression for years. But the challenge is that you can't really compress random floating point numbers. Like, there's not really patterns available to be able to do that. We have techniques to be able to reduce it down, but those techniques are, you're going to lose some information when you try to do that. And finally, there's the query time. So recall that we said we're doing these distance operations, which means we have to compare every single dimension in a vector. Now, there might be some embedding models that say, well, you only have to compare the first 256, but it's still 256 comparisons you have to make. And if you're doing that over 1 million vectors in a data set, that's going to take a lot of time. So we need some ways to speed it up. And the gist of this talk is that there's really no shortcuts. There is a technique that lets us do this called approximate nearest neighbor search, where instead of having to compare a query vector to every vector in the data set, we can approximate it. We can compare it to a subset of overall vectors. And what's nice is that if you're comparing, say, only 5,000 vectors compared to 1 million vectors, like that 5,000 operation will be a lot faster. That's a tautology there. But it adds a new variable, which we call recall. And recall is the percentage of expected results. So what does that mean? If I'm to do an exact nearest neighbor search, meaning I'm going to take my query vector and compare it to every vector in the data set, I would expect it to return these 10 vectors. But my approximate nearest neighbor search might not do that. It might only return 8 of the expected 10. So that gives us an 80% recall. This is a critical measure. This is something we need to hold on to as we go throughout this talk, because we can't do any comparisons of vector search without understanding what the recall is. And this translates into the applications that you're building, because this is going to be the measurement of your search quality. And that's what the name of the game is. How good are my searches, and are my searches good enough to be able to satisfy the business requirements for my application? So one thing, just some general takeaways before we really dive in is what actually impacts how you choose how you're going to store your vectors and search over them. The first thing is cost. Now, cost may not be the deciding factor, but it's going to be an overall factor in terms of how you build your generative AI application, because the database is one piece of the puzzle. And you might actually want to spend more on your database in this case if it reduces your overall cost to the foundation model, which ultimately will be your biggest cost. But something you have to keep in mind as you're trying to decide all of this, because the thing that's ultimately going to drive it is which embedding model are you using and which foundation model or models are you using. Because that's the generative AI portion of a generative AI application. And those decisions do ultimately impact how you search over your data, and in many ways, the quality of the search, which we'll see later. Then, how easy it is to develop, because a lot of times you're rapidly prototyping these applications, and you want to work with something that you're familiar with. Unfortunately, vector search is a feature, so there's many opportunities to be able to develop with systems that you're very comfortable with. And finally, there's query performance and data ingestion, which I kind of coupled together. But query performance, it's what's your target latency. And maybe you need the fastest latency at the best recall levels for the particular application you're working on, and that's fine. Or maybe you can trade off on latency because you're more cost sensitive in some way. And likewise, are you ingesting your data once and building a vector index? Or are you continuously adding data to it? Because that does impact decisions that you make around what what indexing method you choose. So I like to think about this in terms of a triangle. And your triangle is anchored by recall. Probably should have made a boat and had the boat anchored by recall, but recall is ultimately going to drive everything around the decisions, because say you're indexing. Let's say you choose to have an index on it. Well, typically when you build an index, you think about how big is the index and how long does it take to build it. And this is going to be particularly acute for vector searches. Now, what we're going to see is the more time we spend building the index, the better recall we're going to get, but there's a trade-off. It's going to take longer to index the data. Likewise, there's the query performance. And typically query performance, we think about throughput. How many queries can I send per second? Which there's ways that we can cheat on throughput by scaling out the system. And there's latency, which is how long does it take to return that information. Some less ways to cheat there, though. But I could have the best throughput and the best latency numbers and have a recall of 0, which I've personally done in my test. And this is why I keep saying everything's anchored on recall. So if there's only one thing you take away from this talk today, it's no matter what you do, you ultimately have to measure it by recall. And as we go through this presentation, there's some times where I don't include recall, and I will mention that, and I'll explain why I don't and why it matters. So what ultimately impacts your performance metrics? And I'm not going to spend time going through every single one of these. I want to have it up here. But the takeaway is, one, we're actually going to explore all these things in depth throughout the talk, but they're all in tension with each other. For example, while quantization might reduce the overall size of your index, it's going to have an impact on recall and possibly search time if you need to be able to do more searches to be able to get the recall target that you want. So all these things matter. And as you make your design decisions, you're going to have to weigh each of these steps to determine what ultimately do I want to get out of my application. Now, before we dive into Postgres specifically, we do have vector search across many different services at AWS. I'm not going to read through every which one, but this gets into the ease of development and familiarity. If you're familiar with these systems, you already have data in them, great. Choose it and start building out your application on that. But if you're choosing to use Amazon Aurora or Amazon RDS with Postgres today, well, we're about to dive in. So Postgres is a vector store. Now, we kind of think of Postgres as a relational database traditionally, and well, it is. It's been around a very long time. I'm actually about the same age as the Berkeley project, and Postgres also has a very long open source history. It's almost 30 years old, and because of this, because of Postgres' open source nature, there's been a lot of interesting things that have developed, and I'd like to emphasize really the extensibility of it. Postgres is defined as an object relational database management system, but I think of it as an extensible database system because we can add capabilities without having to either get them in the upstream database or fork the database and create a brand new product. And we've seen this today, for example, with geospatial search. PostGIS is used everywhere in terms of mapping applications, and it's just an extension living alongside Postgres. And that's very powerful. And this kind of extends to vector searches, in part because if you think about geospatial searches, you're dealing with 3 or 4-dimensional vectors or 2-dimensional vectors, and they're tiny vectors. And there's actually some very efficient methods for doing exact searches over them. But with vector searches for Postgres, a lot of it, we did need to invent some new things, alongside in an extension. But the convenience is that a lot of the tooling you have for Postgres already works. So effectively, you're just adding a vector data type and taking your tooling and mapping it to that. Likewise, you probably have data in a Postgres database you want to be able to tie into using with your application. Now, one thing I want to hit on a little bit more in depth was that final point. Why ACID? ACID basically gives us some transactional guarantees in terms of how our data is stored. And that's actually very important from an end user standpoint if you require it, because for one thing, if you look at the ACI, there's guarantees in terms of how your data is visible, that once it's committed, it's there, and the next session that reads it has immediate access to the data. And particularly if you're updating data in real time, that's a very important concept. I love highlighting the last bit, though, durability. Every acronym, every letter in ACID's important, but durability, guarantee that your data is stored. That's a very powerful concept, that if your data is written to storage, it's there permanently, you don't need to worry about it. That's probably the most important property of ACID here, and arguably in general, but why do we care about it for vectors? Because vectors are your data, and you're using it within your operational system to be able to solve a result or get a result. So let's switch into pgvector. So pgvector is this extension that brings a vector data type to Postgres. And in addition to the vector data type, it brings all the operations you need to be able to perform these searches, the comparison operations, the indexing methods, and more. It's open source. It's under active development. I'm proud to say AWS is the second largest contributor to pgvector. And it's something that we feel strongly about because it does help enable you to do vector searches within Postgres for all the reasons we just explained. But why use pgvector? Well, vector search itself, particularly in databases, is rapidly evolving. And last year, people were using pgvector because it was there. It's an extension. It's Postgres compatible. It works with existing applications. But we've seen these workloads scale up and scale out in many ways as generative AI is further adopted, and we're able to build more complex applications. So a lot of the roadmap has been focused on making pgvector scale, adding newer indexing methods, being able to support more complicated workflows such as filtering. Again, all of which we're going to explore today, but a lot of this has come from direct feedback, both from the open source community and talking to customers like yourselves to be able to understand what can we do to be able to help support these workloads. So what's happened over the course of the year, or actually the course of 2 years? I'm not going to read through all of this, all of these one by one, but the first part was just, all right, we got to get pgvector to par with what we see out in the world in terms of all the different vector search solutions. And then focus on the finer points, which is really, can we store smaller amounts of information and be able to deal with more complex search patterns, such as where clauses and joins, while still being able to deliver accurate, highly relevant, efficient results. This is, again, an ongoing development. I would say folks are already running pgvector in production. But these are the types of things that we look at, which is making it both as easy as possible and performant to run these workloads in Postgres. Now, the gist of this talk is going to be about approximate nearest neighbor search, because we can understand how to do exact nearest neighbor search. It's searching across all the different data, and ultimately you're going to be bound by the size of your data set, the number of cores you have, and the amount of time you want to spend to be able to compute that. But pgvector offers two approximate nearest neighbor search methods. There's IVF flat, which is graph-based, and HNSW. Oh, sorry, IVF flat, which is cluster-based, and HNSW, which is graph-based. Each of them have their trade-offs. IVF flat tends to be a little bit smaller. It's faster to build, but it might be harder to hit your recall target. And in order to hit your recall target, you might be having much slower queries, whereas HNSW tends to just be overall easier to manage. Most of the rest of this talk will be focused on HNSW because this has become probably, if not the most popular method, one of the most popular methods just in general for vector search. Now, here's just a quick cheat sheet. If which vector search method do you choose? If you need exact nearest neighbors, you don't use you don't use a vector index. There's a little bit of a misnomer there because you might use some other kind of index, like a B-tree index, a GIN index, et cetera, if you can filter your data down. But if you need to search over the entire data set, you can't use the approximate nearest neighbor index. If you need fast indexing, IVF flat, and basically you probably have a very static data set. It clusters very well. And in that case, if you only need to visit, say, like 1 or 2 centers, IVF flat will also be very fast for search. But pretty much for most other things, you're going to end up using HNSW in some way, shape, or form, with exception with filtering. And filtering is going to be the topic we're going to spend a lot of time on today, because it's going to be all about selectivity. If you have data that's highly selective, meaning your filters eliminate most of the rows, you might not want to use an HNSW index. You might want to use a traditional index, which will do this operation very effectively. But if you have low selectivity, you'll probably want to use an HNSW index because it will be overall faster. And the goal today as we go through this talk is to prove that out, to basically show that by based upon your selectivity, you should be able to choose the right index to be able to, one, meet your recall target, but also meet your performance targets as well. And this is going to get into the gist of it, looking at graphs and charts for what are the best strategies for pgvector today. So we're going to do a journey today, roughly in this order. And as a nod to approximate nearest neighbor search, we will go out of order briefly here. But the big thing is that everything's going to start around storage. Now, why do I say that? One thing, I actually came up as an app developer, and I never really thought about pages and page sizes until I became, until I started talking about pgvector. But this is the fundamental storage unit of Postgres, 8 kilobytes. Now, why this is important is because we're going to see that this is the storage unit that we're bound to when we're indexing data in pgvector. And no matter what, effectively our data needs to fit into 8 kilobytes. But this is going to lead into a very interesting situation where we might end up with wasted storage in our indexes. So here's an example of how many vectors I can fit onto a single index page. And we can see that when vectors are small, we can get more of them onto a single index page. But as they get larger, we might only have one on an index page. And there's going to be overhead to that. And what's funny, not funny, but what's interesting is that at the 1,000 dimension mark, or the 1024 dimension mark, we can only get a single vector onto an index page, which means that we're wasting almost like 4 kilobytes of space. Now, what this is going to do is that this could actually end up impacting your storage capacity. But the thing to keep in mind is that you might not necessarily be as efficiently utilizing the storage. It may not necessarily impact your application overall, but it is something, it's something that you do need to be aware of. Now, what's interesting is you might say, well, Jonathan, I've heard that you can resize pages, like the overall Postgres page size, and that is a compile time flag, which most people just keep it at 8 kilobytes. But index pages are not resizable, which is going to lead into an issue, particularly if we're dealing with floating point numbers. There's a little bit of a pun there on the real data type. So once we get to much larger vectors, those actually can't be fully indexed, at least not right now. There might be techniques that we can use to store the original vector, at least in an index page. But for those these days, we'll have to quantize them, which we'll look at a bit later. But you've probably said, hey, Jonathan, I've actually stored data in my vector index before. I've stored like large data in my tables before that, like large text blobs. And there's a system to do that called Toast. So Toast stands for, Toast is a system that lets you store oversized data. So the idea is that once you're beyond a certain threshold, Postgres is able to store that data in basically in a separate table as we're going to see it. And there's a few different ways of doing that. The reason we're actually going to look at these 3 different storage types is that these are all going to play a factor in terms of how we store the data in our table, and they have performance ramifications. So plain basically says, store the vector in line with the rest of my data in the table, and then it's basically all there in one place. External and extended say, store the vector in the Toast table, which after 2 kilobytes in size, it's going to do by default, unless you adjust that threshold. Now, since pgvector06, pgvector's defaulted to using external, which basically means store it in that separate table and don't compress it. Otherwise, we're wasting cycles trying to compress something that we can't compress. Now, let's just visualize that real quick and explain why this matters. So with plain storage, in your table, all the data is stored all together, whereas with extended and external, we're storing the vector in a different page, which is effectively in a different table. Now, the reason Toast was invented was basically we were dealing with data that was not in the hot path. With vectors, we need to search over the vector. That's the key thing we're searching over. But for something like text or other large data where we're not necessarily looking at that, we're not doing the comparison operation on it. It's not in the critical path. It makes sense to store it out of line. But this is going to have ramifications because even though you might still need to use Toast for your data set, we need to understand that there's going to be performance trade-offs for it. In particular, let's look at an example in terms of QPS. So in this example, I took 5,000 vectors and performed a cosine distance against them, of all different dimensions. And we're going to see that after 512 dimensions, performance is going to drop way off if my data is stored in the external format. Because what's happening is Postgres is having to take the data and say, OK, well, it's in this table over here. I have to pull it into memory and then do this comparison. And that's a big penalty. Now, when we're searching the index, we're not going to see that as much because effectively, index pages are stored in a plain format. All the vectors are in line. But if you're computing an index or doing an exact nearest neighbor search, you could end up seeing that. And that could be why, why is it taking so long to index? Oh, it's constantly going back and forth between Toast. So if you know your data is going to be in the hot path, you might want to keep your vector in plain storage. The trade-off to that is you need to make sure that the entire row fits within a single page. And that might be possible, but again, you have to check what your data is there. Now, this also has an effect on query planning. And again, we're going to look at exact nearest neighbors. So here's a query plan, 10 million of 120 dimensional vectors. And we can see that we get 6 parallel workers. Cool. Here's that same query plan for 1,500 dimensions. And we can see we get 4 parallel workers, which makes sense, right? No, why is that less? It should be more. There's more. These are larger vectors. It's going to take more computation time. And the challenge, and it's also it's more data, too. So the challenge is that, the reason we're getting that underestimation is that if you look at the plain case, we can see all the data in the single page. And it looks like, well, that's one full page. But with Toast, the challenge is that we're going to accumulate a lot more data on individual pages, which means it's going to look like it's smaller. Now, fortunately, there's a technique where if you set this parameter, min parallel table scan size, and what's ultimately going to happen is that Postgres is going to then estimate better that, oh, we actually need 11 parallel workers to be able to complete this query. So again, this is important. These are the things that as an app developer, I might not necessarily have thought of. But it's good to have these parameters. So if you're just looking at just storing data in general, here's the guidance that if your vectors could be on the hot path, you want to be able to use storage plain. If it's not on the hot path, you can definitely use the others. And ultimately, Toast is not going to be available for indexing. So now we're going to get into best practices for HNSW build and storage parameters. And I'm going to start here. So with HNSW, storage is going to, our storage strategy is going to matter as well. And it's first going to start from these build parameters. Now, the most important parameter is M, which you probably will not need to modify, but we're going to see what happens when we do modify it and the cases that we will. And then there's EF construction. EF construction is effectively your search radius as you go through the index. Now, notice I say the recommendation here is 64 or 256. So we're going to see why, so 64 is the default, and the default's actually pretty good. You can eke out a little bit more recall of 256, but we're going to see that there's some query performance trade-offs, and we're going to have to see if those are acceptable, because again, like all these are going to be in tension. Now, when I gave the presentation last year, I did recommend 256, so the reason I put in the asterisk as well is I'm walking that back slightly, because now that we have some more data, we're going to see what those trade-offs are. The other parameter that's important is EF search, which is the search parameter when you're going through the query. That's the overall search radius that you're looking over at the bottom layer, which, again, we're going to explore this in depth. Now, EF search was often, you basically increase EF search to increase your recall, but with the filtering case, it was often increased in order to handle over-filtering or not returning enough results. But we're going to see that how with the recent changes in PG vector, that calculus has changed, and we have some more parameters that we can tune for filtering. So what happens when we query an HNSW index? Well, let's start at the top. You come into the top layer. The H for HNSW stands for hierarchical. You find your closest vector at the top layer. You're like, OK, cool. You go down. You find your closest vector at the next layer. You go down. And there might be several layers, right? But so then at the bottom layer, you find your most nearest set of vectors by traversing the graph, and you ultimately converge on your closest set. And it's very efficient. It kind of feels like you're going down a tree, and in many ways it is, because a graph is a superset of a tree. But we're going to find that what's going on with our HNSW index, the decisions we make in terms of how we build and how we search over it will ultimately impact the search time. So what's actually happening when we search it? So first is that we're maintaining a list of vectors that have already been visited, so we don't visit them again and do a costly computation. And by we, this is PG vector. We don't need to worry about this ourselves. Then, as we're going through, we're maintaining an ordered list of candidate vectors. So these are effectively the vectors that are closest to the query vector. So what's cool is as you're going down the different layers of the graph, up until the bottom layer, EF search is 1. You're basically trying to search like a very small radius to try to find what the best possible outcome is. And then at the bottom layer, you're going to spend a lot of time doing the full search based upon what your EF search value is. This actually matters because we're going to see that what portion of the upper layers of the graph can we index in memory. A big thing with indexing is locality or temporal locality, which is the hot portions of your index stay in memory, and maybe the leaf portions or less frequently accessed portions, you go to disk, but you're not searching over a lot of it. But we're going to see that with HNSW, you're going to spend a lot of time searching effectively the leaf portion, which is layer 0. So let's take m equals 16, which is the default. So about 6% of your index is going to reside in the upper layers, which means that you basically are going to only have roughly 6% of the index where you can get that very strong locality unless you're fitting the entire index in memory. The reason that matters is that the more of the index you keep in memory, the faster the search is, particularly because we're going to see the search is actually very exhaustive. Now, you might say, well, fine, then maybe I should make m equals 2 and keep as much of the index in memory as possible. But remember, EF search is only 1 at the top, the top layer, so you're probably not visiting the best candidate vectors as you get to the bottom portion of the graph. So you get placed in a portion of the graph that's actually less than ideal for the search, and you're going to get bad recall, which is why we typically start with m equals 16 with PG vector and work from there. So we can also see that, how does m actually impact the search? And this is actually maybe my favorite slide in the entire presentation. Here's 5 different data sets with 5 different embedding models of actually 5 different sizes. And taking all the PG vector defaults, we can see that roughly we're searching the same number of vectors at EF construction equals 40. And that's really cool. That's actually something that's very powerful in the HNSW algorithm itself, is that it roughly scales. It scales, basically scales in terms of your build parameter m, not necessarily your data set size. And granted that as your data set increases, you will have to search more vectors at these particular sizes. But that's actually something to keep in mind as you're doing this kind of selection, that m is actually going to be the biggest hammer in terms of how many vectors you have to search. And this is the slide that shows that. So here's 2 different data sets, one data set on the left side, one data set on the right. And the 2 columns in between are m equals 16 and m equals 64. And we see that as we modify m, we're scanning more vectors. And again, if we're scanning more vectors, we're probably getting better quality results. But the trade-off is going to be in query performance because remember, it takes about, if we're scanning like 5,000 vectors, we saw it's going to take between 1 and 4 milliseconds. So the more vectors we have to scan, the more time it's going to take to complete those queries. Now, the other thing to keep in mind as well is you probably see, well, wait a second, on the 1,500 dimensional data set, it's taking I'm scanning 2,300 vectors, but on the 768, it's 3,000 vectors. And that gets back to choice of embedding model. The embedding model is going to impact the ultimate convergence of how quickly you're able to get all of that information. And that's important because you need to understand the embedding model and its characteristics as you're choosing these build parameters, because you might end up choosing an index build parameter that ends up taking more time, and you might not necessarily be getting the result that you want. Now, to index all of this information, the index build speed matters because the more time we spend indexing, the better quality index we can build. Now, we see eventually we hit some kind of diminishing return, and it does depend on your implementation, so this is PG vector specific, but we kind of max out around EF construction equals 256. The thing to keep in mind though is if we look at the index build time, if we're just using a serial worker to build the index, we're talking about in terms of hours if we increase EF construction. Now, we might not have hours to wait, but if we use parallel builds, we can see that we're getting the same kind of recall, but it's taking minutes. And this is, again, where you have to decide, am I bulk loading my vectors, or am I iteratively adding my vectors? Because based upon that, I might have to modify either the ingestion method I'm using, which we'll look at a few of those in a few slides, or I need to understand what resources do I have available on my machine, because it'll make a lot more sense if I can do a parallel build and be able to get my data ready in minutes instead of hours. Finally, the other thing is what happens if how does EF construction impact query performance? And this is where I want to walk back a recommendation I made last year about oh yeah, EF construction 256. We're getting the best recall and the best index build time, but we actually have a little bit of a drop-off on QPS. And I ran this test on a bunch of different data sets. I'm showing this one with the just 960 one. And the drop-off isn't terrible. It's roughly 10%. But are you able to afford that 10% to be able to get that better recall? Because EF construction is the easiest way to increase the recall of your overall data set, but it ultimately is going to impact that query performance a little bit. So you have to decide if that works for you. All right. So last but not least, before we get into ingesting the data, the other thing is how does M actually impact index build time and search quality? M is going to definitely improve your recall. Well, definitely is a strong term. With high probability, M is going to improve your recall, but it ultimately is going to have an impact on how long it takes to build the index. And again, this is with parallel index builds, so we're doing it in minutes, but if you don't have a 64-core machine that's building the index, ultimately that's going to creep up. M equals 16 is a great place to start with because it's going to give you, a pretty good quality index, and your ultimate query time is going to be fast. But keep in mind, as you increase M, ultimately your query time will be slower because you have to scan that many more vectors. These are the trade-offs. You have to decide what makes the most sense for your application, but this hopefully gives you the information where you're able to make that decision. So now we're going to talk about ingestion. So what we just saw with index building, we basically had all the data in a table and we built an index. But quite frequently, you're either streaming data in, your customers are adding data in. We need to understand how to ingest the data. So if you're able to bulk load, I'd say bulk load and build the index. That's going to be the best performance. But if you're iterating the data in, if you have the index pre-computed, we need to find the correct method that's able to help us do that. And here's a case where all these methods, we're just doing serial ingestion. We have one worker, one client ingesting a bunch of vectors. And we can see there's a huge difference in methods. Now, bulk inserts seem to be the way to go. And eventually, at least with this data set, there's a diminishing return. Like if I was inserting 1,000 vectors in bulk every single time, that basically was the magic number. But you also see that if I'm just doing a serial insert, it's taking a long time. And if you're like, oh, hey, this is taking forever, that could be why. The other interesting one is copy versus copy binary. So copy is a Postgres command that helps you to rapidly ingest data. It's something that you learn early on. But we're going to see that there's actually challenges with just using copy without the binary format because it actually becomes an expensive operation. So this is copy. And what happens if you're just using copy is that you'll take a binary formatted vector, convert it to a text representation, send it over the wire, Postgres gets it and converts it back to the binary format. That's expensive because particularly if your vector is 1,500 dimensions, you're basically converting from 1,500 floats to 1,500 text values back to 1,500 floats. And I've literally seen my machine crying like trying to do that. With copy binary, you're barely doing any work there. And I've seen in some cases 3-4x faster ingestion speed just by using that method. So if you're bulk loading data, you're doing a serial insert, you already have your vector index, you have two options. So bulk inserts and copy at the binary format. It gets more interesting as you add concurrency. Let's say you have multiple ingestion jobs. What's interesting is you start to get some diminishing returns. Insert actually starts to look pretty fast without doing a bulk insert. You probably still don't want to do it because it does take more time, but concurrency kind of masks some of the issues that you might have with serial load. But that said, the other methods do hold up. And in fact, copy itself, well, two fun things. One, copy without the binary format, regular copy seems to look pretty fast at that point. But also, we don't get that much faster with the copy of the binary format once we get beyond one or two of the workers. So some things to keep in mind when you're ingesting. But the final bit, again, just to prove the point that if you can build your index all at once, do that. You can't beat a create index with parallel builds, particularly with pgvector's memory improvements, starting with a version 0.6 and then with 0.8. It's pretty fast. So if you can bulk index build, do that. If not, you have a bunch of different methods you can use. So to summarize, what are the best practices with HNSW? Start with the defaults. I actually have been seeing some issues in the pgvector repo where folks don't use the defaults, and I'm actually working to drill in on those more. But it might end up into some issues that if you don't have enough information to troubleshoot, around query performance, you might not know what to do. But the defaults are pretty good. If you need to boost recall, again, jump up to EF construction equals 256. In general, if you're able to use plain storage on your table data, that's going to maximize your performance. And with ingestion, make sure you use the appropriate ingestion technique. Bulk inserts or copy of the binary format, that's going to help you go very fast. Finally, quantization is a technique that can help you to reduce your overall storage, which we're going to touch on real quick before we get into filtering. So what's quantization? Quantization is effectively another transformation of your vector. If you have a 4-byte floating point vector and you say quantize it to a 2-byte floating point vector, that's a type of scalar quantization. And you can keep going down the list, all the way down to binary quantization, where you're taking a 32-bit value and turning it into 1-bit. And that's a very extreme form because you're losing a lot of information there. Now, these are very effective storage techniques, but they have trade-offs. First thing I'll note is that Postgres has this concept of expression index, where if you have an immutable function, you can basically use that function to map data into an index. And that's pretty cool because for scalar quantization, all we're doing here is we're basically taking our 4-byte floating point vector and mapping it to a 2-byte floating point vector. That's pretty cool. To actually implement this in pgvector did not take all that much work. Same thing with binary quantization. There's a function in pgvector that does the work. But with binary quantization, we're losing a lot of information. So ultimately, you're going to need to run some kind of query like this to be able to use the index search to efficiently look over the data and then ultimately re-rank it. Now, coming as an app developer, it might look a little bit scary. You could also do this with a common table expression. I got used to writing subqueries like this, but the main takeaway is that you will need to do some re-ranking if you're using binary quantization, unless your embedding model is a binary embedding model, in which case you don't need to do this, and you're going to have some very fast searches. So what's the ultimate impact? So here's a test over a particular data set, 5 million, 1,500 dimensional vectors. So we can definitely, left-hand column is the original vector, then 2-byte floating point vector, and then binary quantized vector. And we can definitely see the size difference, and we can see the index build time difference. It takes a lot less time to be able to build a binary quantized vector. But we see the impact on recall. Definitely the binary quantized vector is faster, but at the same level EF search, it has much worse recall. And eventually, we can be able to improve recall. Remember, EF search is one of our levers. And again, the binary quantized vector, doing that search will be faster. Again, what is your recall trade-off? Is this going to be good enough? You get a faster search, smaller index. You'll be able to keep more in memory. But it's going to be about your search quality at the end of the day. So you have to decide, is this trade-off make sense for you? So the thing with quantization is that the takeaway is it's going to involve information loss. You need to make sure that your team is OK with that, and you need to test. You need to make sure that you're getting the results that are most relevant. The other thing is, as you add more data that's quantized to your index, you're going to get values that look very similar, particularly binary quantized values where you're going to have similar bit strings, which means you'll have to search over more of the index to be able to get better results. When I was originally testing binary quantization with pgvector, I used the GIST960 data set and that particular function in it. And I was getting the fastest results I'd ever seen from pgvector. And I went to look at my recall, and it was 0. So this is why it's very important to understand what is going to be the impact of these methods on your search quality. And now the fun topic, filtering. This is the part I'm most excited for. Why? Because it's a simple query. We've run this, we've probably run this a million times in your database. But it has a really interesting impact with approximate nearest neighbor search. So what happens? If you have a where clause in your query, Postgres is going to make a choice. The query planner is going to decide, well, maybe I'm not going to use the index. I'm going to use something else. Or I'm going to use the index, but I don't get enough results back, which is the overfiltering problem, which is incredibly frustrating. Or you might get a post filter, which could be OK, but depending on your selectivity, that could end up being very, very slow because you're basically searching through the table and trying to filter all the results based on those values. Now, how do we decide our filtering strategy? This is going to be very important with the latest release of pgvector 08 because you have so many more options to choose from. First is your query patterns. How many of your queries are filtered queries versus unfiltered, where you have to search through the entire vector index? If you know that you're never going to be running a filter, OK, easy, use an approximate nearest neighbor index. If you know your filters are highly selective, don't use an approximate nearest neighbor index. It'll make it much easier. Because that's really going to be the key here. Selectivity. I never, ever thought about selectivity until I came to the DBA side of things. As an app developer, I'm like, oh, index makes things faster. But index makes things faster because the data I was dealing with was very highly selective. It was filtering most of the rows down. And that's going to be ultimately the key. How many vectors are we going to be comparing? And this is going to go back to that slide we saw a lot earlier, which is, we know that 5,000 of these distance operations on the R7i for these size vectors take this much time. This is a good benchmark because we see that a lot of the queries involving, let's say, HNSW scans will probably be within the bounds of 5,000 computations. Now, the QPS here, this is actually going to be our upper bound on all of these vectors. So here we're using a table scan. So we know that in our table scan, if I'm comparing 5,000 vectors, my upper bounds could be 5,000 queries per second, or 500 queries per second, or whatever it is. And that's going to be important as we're looking at the different filters, because if we know this is as fast as we can get, then we can decide how, are we going to use an approximate nearest neighbor index? Are we going to use an iterative scan? Are we going to use a B tree? Now, before pgvector 08, you really had two methods to be able to do efficient filtering. One was creating a partial index, where you put a where clause on your index, or you could partition. And again, these techniques work. I've worked with customers who are doing this at billion scale in production, but it involves more management and maintenance, and you really need to thoroughly understand your data set and how it works. But since pgvector 08, which was recently released, there's more. There's two changes that ultimately impact filtering. First is how the Postgres Query Planner estimates an HNSW scan. Before this release, it was underestimating how much time it would take to scan an HNSW index. And all those charts that we saw earlier were actually the data that helped drive getting a much better estimation for how long it would take. Because if we determine an HNSW index scan is going to take too long, let's do another kind of scan. But there are definitely times where we have low selectivity, or a filter is going to eliminate some rows, but not all the rows, or not to a very small size, where it does make sense to use an HNSW index and do a post filter. So we need to be able to solve that over-filtering problem. And this is where the HNSW iterative scan parameter comes in. So if you select this parameter, if you're going through an HNSW index and you exceed your EF search and you still haven't satisfied the limit, it's going to keep scanning. And that's really important because it's going to be able to return enough results to satisfy your satisfy your filters, as long as you're able to meet that max scan tuple size. So let's make it less abstract. So here's a data set which has 4 filters involved in it. I believe it's 5 million rows, and they each have different levels of selectivity. So here's a query, here's code, and here's the query to perform a nearest neighbor search where we have different levels of selectivity. So 10% selectivity means that 500,000 rows here match the filter. 1% 50,000, 0.1% 5,000, et cetera, et cetera. This is probably something you've seen if you try to run these filters, is that if you're highly selective, you run this query and you don't get enough rows back, or you get no rows back, and that's a very bad experience. Now, up until then, up until this release, there really, the one toggle that you had was that you can increase EF search up to the max, which is 1,000. But the problem is that while it will solve the case of low selectivity to a degree, it's still not great. You could still end up with overfiltering. And if you have high selectivity, forget it. You're not going to get enough rows back. And on top of that, your performance is going to be very slow. But we have a new tool. We have this iterative scan feature where the scans will keep going through to be able to solve the problem. And what's nice is that not only do we get enough rows back, we're actually getting better performance than what we would have with EF search equals 1,000, because here we're using EF search equals 40. However, if you're highly selective, meaning you're not returning enough rows, the iterative scan not only will underperform, you're still not going to get enough rows back because you're probably meeting the max tuple scan. You're at that point, which is 20,000 tuples. But keep in mind, you probably have about 500 vectors that match that particular filter. So this is where a B-tree comes in. Let's say we compare the iterative scan method to the B-tree method. And what makes sense is that if we have low selectivity, an iterative scan will be much faster. But if we have high selectivity, a B-tree is going to be faster. It's going to be super fast. That's getting faster results than what we were getting with some of the examples before. And that's really cool because if you know that you have high selectivity, a B-tree is going to work and it's going to be able to get the results back that you need. Now notice that in the case of 0.1% selectivity, we weren't always getting 10 rows back. And that was probably a little quirk where the query planner saw that the HNSW index was probably the better one to choose. And based upon that cost, it was going through and choosing that. And this is where I say vector search is an evolving topic that I'm sure we're going to continue to get those cost estimates better. Now finally, multi-filters. Multi-filters are fun and something that comes up quite often, like where A equals 1 and B equals 2. So here's a test where we did a multi-filter with these 2 levels of selectivity. We tried 3 different ways of doing it. First, the iterative scan method, then a B-tree multi-column index, which is the first example, and then just putting all the data in a JSON column. So the results are interesting. First is that we're able to get all the rows back. So again, that's your upper bound on your recall. If you get 10 rows back, your recall could max out at 100%. But the performance numbers are also interesting because one, we're able to get good query performance with the multi-column index, and while the JSON numbers weren't as good, the thing I want to point out with putting these filters in JSON is if you don't have well-defined filters, like you don't know if you're going to always search like A and B, it could be any number of 100 or 50 or whatever filters. JSON using the Postgres JSON type is a good catch-all for that, and you can still get decent query performance, but it likely won't be as good as a B-tree. Now, finally, this isn't like an either-or statement. The nice thing is that you can have all of these all at once. You might not want to have all of them all at once because there's index maintenance costs for that, but you can keep them all together. And in general, these other indexing methods are going to be a lot cheaper to maintain than HNSW because they're infinitely smaller. So finally, best practices in filtering. As someone who's been staring at vector search for a lot over the past 2 years, here I'm telling you that if you don't need to use a vector index, don't use a vector index. Use one of the other indexes. If you have a mix of selectivity, you can mix and match. You can have an HNSW index alongside a B-tree index and Postgres will make the intelligent choice in terms of the one that's going to make the most sense to satisfy the query. And finally, there's still the old hammers of partitioning and partial indexes. If you know that you have, you're able to segment your data, the data is lowly selective, it might be still better to put those into the particular partitions and then further refine it from there. Now, we're starting to reach the end of the session, so I want to talk a little bit about some of the Amazon Aurora features that can help benefit vector search. So first, if you're not familiar with Amazon Aurora is our commercial database that provides MySQL and Postgres compatibility and offers all the features that you would expect that you need to be able to manage your database workloads. I like to think of it as, going back to my app developer roots, I don't want to think about managing the database. I just want to be able to build things and have it automatically scale with me and meet all my different security and compliance properties. Now, some of these features specifically benefit vector workloads. First feature, Amazon Aurora optimized reads, which basically lets you use the local NVMe, which serves as effectively a tiered cache. So if I have data that is clean, or if I have data in memory, it has been modified, and it gets evicted for whatever reason, instead of having to retrieve that page again from storage, that page will actually go to the tiered cache that's residing on the Aurora instance. And the benefit is that when you try to recall that page again, you don't have to go all the way down to storage. You only have to go to the local NVMe, which we'll see in an upcoming slide has some performance benefits, particularly for highly concurrent workloads. It also helps you scale that workload on your same instance size further. There's also higher memory instances in Aurora, being able to use, for example, the R7Gs and R7Is, so you can keep more of your vector data in memory. And as we've seen, vector data, particularly the index vector data, can be fairly large. And if your workload does exceed a single instance size, there's Amazon Aurora Postgres Limitless, which will automatically shard your data across multiple instances. There's also the builder features that if you want to be able to simply connect your data, whether it's data residing in your Amazon Aurora database to embedding models in Amazon Bedrock, or vice versa, you have an external data source that you're transforming into vectors and putting into your Aurora database, there are these features for that. And finally, just general compatibility, because Amazon Aurora is Postgres compatible, a lot of builder tools already work with it. So let's make the optimized reads slide, or the optimized reads feature more tangible. So this is a workload where we had 1 billion vectors, and we were running it on purposely smaller instances to make sure it couldn't fit into memory. And we took a Amazon Aurora standard I/O instance and an Amazon Aurora optimized I/O with optimized reads instance, and we kept increasing the concurrency and trying to see which one performed better. And it turned out that the optimized reads instance was 9x faster, particularly when we were really thrashing the memory and trying to call things constantly in and out of memory. And again, that's where having that NVMe layer helps, because instead of having to go all the way across the network to retrieve the page that is evicted from memory, we only had to go to the localized NVMe. And just a quick call out to Amazon Aurora Limitless. Again, if your workload is exceeding the available resources on your system, say you're writing too much or it doesn't fit all in one instance, you can use Limitless to be able to store the vectors across multiple instances. So Amazon Bedrock Knowledge Bases, this is the way that you can automate your pipeline, where if you have vectors, say in an S3 bucket, so not vectors, if you have documents or other data in an S3 bucket that you want to search over for the benefit of RAG, you can tie into a knowledge base, which is automatically managing that pipeline of data and inserting it into Aurora database. And then you can connect it up with Amazon Bedrock agents, where the agents where you define your workflow and ultimately how you tie it into your application, and it will automatically query the database, so that way everything is fully managed. Now, let's look a little bit ahead, what's coming next in terms of pgvector. Well, as I mentioned, filtering is the hot topic. You can probably tell I'm very excited to talk about that. And all that data was data that has been just shared for the first time today. But there's more to do on filtering. One of the big areas is pre-filtering, which is the idea that you can store your data you need to filter alongside your vector in an index and then efficiently go through that. This is an area that's still being actively researched, I'd say, in general. I don't know if there's some techniques that seem promising. I don't think there's a clear winner yet. And one of the pgvector promises is similar to Postgres. We don't want to change the underlying data format and cause you to have to do a costly reindex on an operation like that. So part of it is waiting to see what are the techniques that emerge that will be the most effective, and then we'll support one of those. There's more dimension data types likely coming. There's patches open for both 1-byte floating point vectors and 1-byte integer vectors. If those are useful, please influence the open issues. Streaming I/O. Streaming I/O is a Postgres 17 feature that lets you literally stream I/O, basically load I/O in bulk from your disk. We've been doing some early tests on it to see if it could benefit pgvector. Definitely on the IVF flat method, where when you're reading from disk, there's a lot of streaming blocks that you need to read in. It could also work well with HNSW, but you likely would see more benefit for IVF flat. As well as additional quantization techniques, statistical quantization looks promising, and supporting parallel query as needed. So this was a fairly long, intensive talk. Thank you for bearing with me through it. As I said, it's a lot of graphs and charts, but hopefully the graphs and charts help give you the information you need to make the appropriate decisions around your application. I know there are some 300-level talks that will tie all these pieces together, but this is the one where if we really dive in and we understand how it works, from a Postgres standpoint, you should hopefully have strategies now to help make the decisions you need in terms of how do I store this data, how do I index this data, what are ultimately the design decision trade-offs I need to make. And it's going to come down to this at the end of the day. First thing is recall. I should put recall first on the slide, but it's recall and query performance, because that's ultimately what you're delivering to your users. Your users are going to see the quality of the searches, and they're going to see how quickly they come back. And once you understand what those targets are, then you know where to invest. You have to make investments in infrastructure in as much as you're making investments in your schema design, your application design, et cetera. There's features Amazon Aurora offered that will help you scale and simply build your workloads. And as I said as I think I said at the beginning of the talk, I gave a similar talk last year, and I pretty much rewrote the entire thing. Some of the slides are similar, but this also means that you got to plan for today and plan for tomorrow. Vector search in general is getting more stable in the database space as a whole, but there will be more innovations. There's more algorithms being developed. I think pre-filtering is going to be an area that's going to be very exciting probably over the next year. But the technology is mature now for you to build your production level applications, and the goal of this talk was to give you the tools you need to make those decisions. So with that, thank you very much, and thank you for attending today.